the record, and then come back up here. I think this should update. Right, where's all my pictures? Picture. Keep going down. Right, so that's this Friday in this room at 2, right? And on Canvas there should be assignments for, and as each of the seminars you come and you just write a little summary of it, and you get 20 point extra credit for coming and just writing a summary. And usually we'll have pizza and sodas. Yeah, what's up? Next week it's also going to be 2, the same time, on Monday, because next Friday, right, that's actually the 31st, which is Cesar Chavez Day, so we don't have school, right? So we're going to have it on Monday. The reason we have it on Monday is that I know you guys don't have labs on Monday, right? So you have no excuse not to come next Monday. You have lab? In general physics?
Yeah.
No.
Yeah.
He canceled it. Well, he said he doesn't have lab next week. That's when I talked to him. He didn't tell you guys that? Okay.
Thank you.
Yeah. Yeah. Okay, I'm gonna double check with him, and he should not have lab. Okay. And so next Monday's talk is actually going to be on atmospheric science. So you get kind of a taste of different type of sciences. And Dr. Takihashi actually works also in Europe. So she's flying in from France to give us a talk about her work. So and every time you show up, you write a little summary. You get a little bit extra credit for the class, and hopefully that's helpful. We'll see how the next midterm goes, right? I think you guys know what to expect now, right? Right? They're going to be getting to the concept and getting the starting equation is the hardest part, right? And then when you do the math, and if you run into a lot of math, that means something weird is happening, right? So I'm trying to make the math as quickly as possible. Okay. And talking about math, that's going to be hard. Remember this? We did this yesterday with a straight wire, right? You would think this is the simplest thing, right? Where we try to calculate the magnetic field, some point P, Y above the wire, right? We're just trying to calculate what is the magnitude of this magnetic field if you have a wire going like this, right? As usual, right? Just like you did in your worksheet today, right? We start off with a little tiny segment of wire, right? When segments are tiny, there's no curvature to it, and you don't have to worry about it, right? So you start off with that, and it just turns into this long, I think it took me like 20 minutes to get through this yesterday, right? Long, derivation that changes the from a tiny wire to sum up the tiny segment, and then to get the magnetic field from the entire wire, I have to add up all the little tiny segments along that wire, right? And that's where the summation comes from, right? And then when we take the limit as delta x goes to 0, it turns it into an integral. And this is where I think I forgot how to do that integral, and I have to scroll up to figure it out, right? But if this was on the test, I'll give you this integral, right? But it'll be on the side there and say, oh, how do you do that? Okay. And then we'll figure out the magnetic field from a wire, right, at some point P above the wire, and it's actually basically this constant. Of course, it's going to be proportional to the current, right? If there's no current, there's no magnetic field. And there's this 2 pi thing here, and the reason for the 2 pi thing is when we did the integral, we end up with a factor of 2. Okay, and it's inversely proportional to y, right, as we expected, because the further you are away from the wire, the weaker the magnetic field, right? This is one of the things we observed in the first lecture during the experiment. You have a question? Oh, so hands up. Okay, so now that's the hard way to do it, and I'm going to show you guys the easy way to do it with certain symmetries. Okay, remember when we did this stuff with the electric field? It was really hard also, right? But then what do we come up with to make some of the how do you calculate electric field in an easier way with problem that has a lot of symmetry? Do you guys remember how to do that?
Gaussian surface.
Right, Gaussian surface, or Gauss's law. Okay, and of course Dr. Gauss, or whatever his name is, whatever his title is back then, it's probably like Lord Gauss or something like that. Didn't study current, but this guy, Ampere, right? Hence the name for the current, the units for current. This guy Ampere has a way to calculate magnetic fields from a wire or a charge, right? That is much simpler, okay? But before we can do that, we have to introduce a thing called line integral, and we're going to talk about what that means, okay? So let's say we have a wire, right, that's going along in this blue magnetic field, right? And this magnetic field is not constant. It's like something random, okay? So it obeys some function, and we're going to start our little path here from initial position, and we're going to follow the little charge, and then we're going to follow it all the way to the end to the final position, okay? So in order to figure out how much of this path is following the direction of the magnetic field, okay, we do this thing called a path integral. I think the book didn't want to scare you guys, so the book called it, we're just integrating the magnetic field along the line, okay? So the technical math word for it is known as a path integral, okay? So the way you do this is you pick a little tiny segment, just as like, it seems like all of physics is just like, oh, you have a very complicated problem, you take a little tiny piece of it, solve that part, right, and then you add up all the solution, right? And take a little tiny piece of it, right? And since you have a tiny piece of it, you can just treat that little segment as a straight line, right? Because you know the closer and closer you stare at an object, right, it's straight, right? Just as we're on the Earth, it appears flat to us because we're so close to the surface of the Earth. Okay, what we can do is that while at that particular little tiny segment, we can calculate the vector delta S and the subscript K, because we're going to add up a bunch of them together. And this particular position, it also has a magnetic field sub K, right? We don't know what the value is, but then it'll point in some direction, right? Okay, right? If we're trying to figure out how much of the magnetic field is going along this path, right, we actually want to figure out the dot product between the two, right? Remember, dot product tells you how parallel two things are. Cross product tells you how how perpendicular two things are. So what we're going to do, okay, we are going to sum up all the little magnetic fields, dot product it with this little segment, little wire segment, delta S, okay? And as usual, if we take delta S as the limit of delta S approaches 0, this turns it into an integral of B dot ds, okay? And this is known as a line integral of the magnetic field from the initial position to the final position. So that's all the mathy stuff, okay? Okay. So and once again, we have this integral dot products with vectors, right? And those are like complicated math stuff to deal with, right? And if you decide to major in physics, you get to do that if you want, okay? In upper division, electricity and magnetism, okay? If you want to do that. I mean, I went through it, did like 3 years of it, probably forgot like 99% of it, okay? But in this class, okay, we're going to do the easy version, okay? So there's a lot of different problem with this, where the symmetry of the problem or the geometry of the problem makes this calculation very easy, right? So let's say your magnetic field is always perpendicular to your path, right? The dot product between the two vectors that are perpendicular to each other is always going to be 0, right? Right? Dot product tells you how parallel two things are to each other. So if your magnetic field is always perpendicular to the path you're traveling along, right, the integral is 0, right? That's pretty easy, okay? Or, right, the other version, the opposite, right, let's say your magnetic field is always along the path anyway, right? Therefore, when you want to calculate that integral, right, what you can do is that, well, if this also assumes that the magnetic field is constant, right? It's actually the magnetic field strength times the distance, or this L. L is the length of the path, okay? The length of the path, okay? Right? Not the distance between the two. Remember the difference between these two quantities? Right? If I calculate the distance between these 2 points, it's going to be shorter than the length along the path, right? So it's actually the length along the path that's actually important, not the distance between them. Okay? Any questions about this mathy introduction stuff? Okay, we're going to deal with mostly with these two cases. Okay. Now we're going to introduce Ampere's law. Okay. So just as when we talked about electric fields and Gauss's law, as you guys remember, right? I think the thought experiment we had was that, let's say we have some random box, right? And we know that there's some electric field coming out of it, right? Okay. We can deduce that there's probably some sort of positive charge inside, right? You guys remember that idea? Right? If there's electric field going into it, what kind of charge do you think is going to be inside that box? Negative. Okay. So we're going to do something similar where, well, we're going to have some magnetic field going around, right, without even knowing what the wire is doing. Okay. And we know that the magnetic field is going in this direction, right? That means my hand has to curve in that direction. Right away, I know that the current is actually going into the board, right? Just from the direction of the magnetic field, right? I don't have to look at the wire, right? I know that, oh, if there's some magnetic field going on in this direction, there has to be some sort of current going into the board, okay? And this is the idea of Ampere's law, which, you know, he basically stole from Gauss. So therefore, let's say at some radius r, little r here, right? We want to figure out what is the magnitude of the magnetic field along this circle. Okay, what we're going to do, see if we can do this, right? We're going to create what's known as an Amperian loop. Let's call it the Ampere loop. Okay, this black line here, okay, this is the analogous to the Gaussian surface. Remember, the Gaussian surface is actually not a real thing, right? You can make that up, right? You can place the Gaussian surface wherever you want. This is known as the Amperian loop. Okay? We have some wire, right, that has some current going into the board. We want to figure out the magnetic field some distance r away from it, right? It took me like 20 minutes to do it last time. Remember that? Right? And we're going to see if we can do it today without me taking 20 minutes, because I only have 10, right? So the Ampere's law is going to state that, that the integral of B dot ds, right, is going to be, there's going to be some constant. I think the mu naught is in the top. Mu naught times the current inside the loop. Okay, just like Gauss's law, it only cares about the charges inside the Gaussian surface, right? Okay, all right. So we have some equation, some complicated equation on the left-hand side, and then I'm not sure what's going on the right-hand side here, right? Okay, so let's deal with the left-hand side first. Okay, since we're going around on a circle, we expect that it's all along the circle we are the same distance away from the wire. So this system has this circular symmetry, right? So all of the magnetic field should have the same magnitude. They're all in different directions. The magnitudes are the same though, right? Do you guys agree? Well, maybe, right? And, right, okay, this little ds, right, is the path on the loop, right? It's just this path on the loop. And this path on the loop is always going to be in the same direction as the magnetic field, right? So the dot product between them should be what? Well, you can say either 0 or not 0. Not 0, right? It's not 0. In fact, the dot product between them, right, is going to be, just as we saw up here, right, the magnetic field times the length of that loop, okay? What is the length of a circle? I'm sorry? 2 pi r is the circumference of the circle, right? Right. I'm going to do this in 2 steps. So the magnetic field times the length of the loop, and the length of the loop is just the circumference, right? This is going to be 2 pi little r, okay? The other side, right, tells you how much current does this loop encloses. How much current is inside this loop? Well, it's just I, right? There's no other current around. So solving for the magnitude of the magnetic field is mu naught I 2 pi divided by r, where r, right, is the distance you are away from the wire, right? Let's go back up to here, the thing that took me 20 minutes to do and now took me only 2 minutes, right? Let's go back up here, right? Is this the same result as what we did yesterday? Right? Right? The magnetic field from a wire is mu naught times the current, which is the same here, divided by 2 pi, even got that 2 correctly, right? Divided by y. Why is it y, the other one r? What's the difference? Right? Right? Is y is the same thing as r in this case? Because remember on what we did today, so we're looking down this direction, right? So this is actually the same as the radius of the loop, right? So if I draw a little circle, an Amperian circle around this, right, this will have radius equals to y, right? Right? All along this, it will have the same radius, right? R, right? Okay. So I was able to do the same problem in 2 minutes that took me 20 minutes yesterday, right? Using Ampere's law, okay? So guess what's going to be on the exam, right? Which version you should, or which version should you do on the exam? Okay. There are some problems that you're forced to do it the hardcore, integration way, but with the symmetry of this problem, you can do this pretty quickly. Okay. Any questions about this? How, just from looking on the looking at the left side of the equation, trying to calculate this, and then looking at the right hand of the equation, trying to calculate this, and then you just solve for B afterward. Yeah, Alan?
So the current, does the length of the wire have anything to do with the magnetic field?
So if this wire was very short, what's going to happen is that there'll be um, some asymmetry, meaning some of the magnetic field will actually go into the board, some will go out of the board, right? But this particular case, we're making an assumption that it's like a very long wire, okay? At least the length of the wire has to be much bigger than r. That way, you're not dealing with magnetic field that's going in or out of the board. Because if you have a wire that's sticking out like this, right, more of the wire will be on this side, and then it'll actually go into the board. But if you make them very long, right, on both sides, right, they have this symmetry to it, so they cancel out. That's a good point that I didn't bring up. All right. So the magnetic field, just as we expected, right, along a wire, right, goes around a circle like this, okay, and right, the magnitude can be calculated by just the what is this thing called? Permittivity, the magnetic constant, right, times the current divided by 2 pi divided by r, okay? And this is all, you can do this in 2 minutes using Ampere's law, or you can do this in 20 minutes using integration, okay? Whichever ones you want, okay? Okay. A little bit more detail about Ampere's law before we wrap up today, right? Remember the right-hand side of Ampere's law, right, is mu naught times I inside the loop, okay? That means, let's say you have a more complicated system like this where you have current 1 going this direction, current 2 going this direction, current 3 going this direction, current 4 going in this direction. And I'm interested in calculating maybe the magnetic field at this point, okay? And I make my Amperian loop like this, okay? Usually you won't make it this complicated. You probably want it just a regular circle. Okay? If that's the case, right, the current inside the loop does not include I1, right? Because it's outside the loop. So this has no contribution at all to IN, okay? Don't include that, okay? Right? Now, there's also another complicated thing. Well, another caveat, and let's not call it complicated, right? In this case, we have I2 going this direction, I4 going this direction, I3 going the opposite direction, okay? So if we pick the sign so that, well, this is considered positive current, right? I3 will have to be considered a negative current, right? When you put in that value, you're going to have to put a negative sign in front of it. Make sense? Okay? Right? So when you're calculating IN, you basically have to just figure out, pick a direction. It doesn't matter what it is. Because, right, if once you pick the direction of your current, your right hand tells you which way the loop has to go, right? So if we pick this to be positive, right, we want the loop to go in this direction, which is what the path is doing, right? Okay. So in this case, this will be considered negative current. These two will be considered positive current. Make sense? Okay. All right. I don't think, maybe I can do this in 2 minutes. Yeah, actually I can. So I'm going to do another example using Ampere's law that would take you maybe, like an hour at least if you didn't use Ampere's law. Okay. Just as we did with electric field, we can actually calculate the magnetic field inside a wire also. Okay. So this wire has some current I going through the entire wire. Okay. And has some radius r, and we want to figure out what is the magnetic field inside this wire at some radius little r outside it. Okay. Sorry, inside it. Okay. So since we have the setup for the drawing, okay. One more thing I want to be able to set up is also, let's not do the setup. Let's just chug away and see if we what's missing, because we're going to be missing something in order for us to do that. Okay. Right. So the left-hand side of Ampere's law, just like the other case, right, we have a constant magnetic field going around in this direction at some distance r, right? So this is just going to be B times L once again, where L, right, is the circumference of a circle with radius little r. Okay, so the left-hand side stays the same. Okay, the right-hand side is more complicated because the right-hand side is not I anymore, right? Because you're only including a fraction of the current, right? You don't have the entire current. Remember, we're not allowed to include the current that's outside the loop in Ampere's law, right? So how can we figure out the current that's only inside here, okay? This is where the complication comes in. So instead of calculating I straight, what I want to do is actually calculate the current density, J. Remember this? Right? The current density in this wire, right, is the current going through this wire times the area of the cross-sectional area of the wire, right? So this is I divided by A, right? The area, let's call it area, right, of the entire wire, right, is big R squared times pi, right? It's pi big R squared, right? To calculate the current that's actually inside, so this is another I in, to actually calculate what we want to take a I in, it's going to be equal to the current density times the area of the inner part of the wire, right? That's why A is nice, because I don't have to write all that stuff. A in, okay? Well, J we already found here, right? I over pi R squared, right? A in, right? What's the area of the inner part of that wire? That's pi times which R? Big R, little r. Little r squared, right? The pi's actually cancel out. So In, right, is actually equal to just the regular I, R squared divided by R squared, okay? And now I can plug that in here, okay? That's going to be I, R squared divided by big R squared. I forgot to bring mu naught around, okay? Don't forget mu naught, okay? So solving this equation for B, right, it's going to be mu naught I R squared over 2 pi R big R squared. One of the factors of R cancel out, so this is actually mu naught I times R divided by 2 pi big R squared. Okay? Okay. Okay. And if you want the also signify the direction of it, you can just put a, so this is a counterclockwise, right, direction, right? So you can put a comma counterclockwise. Okay, that's the direction of it. All right, cool. You guys like Ampere's law? Preferable over all the integral and the stuff, hopefully, maybe. it is a harder concept, right? You have to deal with something on the left and you have to deal with something on the right, right? But it makes the math easier, and I love making the math easier, right?